Welcome back everyone. In the last class, we were looking into how to plot approximate Bode plot for a system. We noted down a few pointers based on the factors that are present in a transfer function. Today we are going to use those pointers to come up with the approximate Bode plot of a transfer function. Here is the complete table that we had gone through in the last lecture. Corresponding to different factors, we have different magnitude lines corresponding to different slopes. Similarly, for phase plot, we have different phase angles or different slope corresponding to the phase plots, and we are going to use these today for a particular example. So, I will go ahead with only one example and then I will add a few in the assignments for you to practice. So, suppose this is the example given to you, you have a transfer function given to you. Now, of course, the question is how do I find this transfer function? This you can find out with one of the methods that we have already discussed, basically using the step input and then feeding it into the system and then trying to use the functions that we had shown in one of the lectures and try to estimate what is the transfer function of the system. So, by whatever means you came up with the transfer function say, and now we want to find out the Bode plot for it. Why do you want to find out the Bode plot? All this we will take on later as we move ahead in the course. However, let us just blindly try to find out the Bode plot for this system. So, first of all, what we will do is we will convert this system into the form 1 plus j omega t or 1 by 1 plus j omega t. We will try to convert these to these type of forms. So, that is why what we are doing is we will take 4 common out here, here of course, this is 1. So, here we will take out 36 common. So, once you take these things out as common factors and we will replace s by j omega and we will be left with something like this. So, this is the form in which we have found out those factors, if you remember. So, now let us use each of these to come up with a complete approximate Bode plot for this system say. So, what are the factors here? So, the first two factors that we are concentrating on are these two factors 6 and j omega. If you remember, corresponding to a constant, so there is no frequency because corner frequency, because for a constant factor it is just a 0 dB per decade line passing through 20 log of 6. In this case q equal to 6. So, we have 20 log of 6. So, it is a 20 log of 6 straight line which does not have any slope, it will be parallel to the x axis. Now, 1 by j omega is a minus 20 dB per decade line. So, as a whole, if you notice, if I take both together and check what is the magnitude, this is what the magnitude will turn out to be, which is nothing but 20 log of 6 minus 20 log of omega. Now, that means corresponding to these two factors together 6 by j omega, these two factors together, it will be a minus 20 dB per decade line, because here there is no slope, 0 dB per decade line, this is a minus 20 dB per decade line. If I take both together, it becomes a minus 20 dB per decade line and it will pass through 20 log of 6. When I put omega equal to 0 here, you will see that the magnitude comes out to be 20 log of 6. So, at omega equal to 1 radian per second. So, if I put omega equal to 1 here, then it becomes 20 log of 1 is 0. So, we get the magnitude comes out to be 20 log of 6. So, it is a minus 20 dB per decade line which passes through 20 log of 6 at omega equal to 1 radian per second. So, if I take both together instead of writing them separately, so we can write it like this, say 6 by j omega, the contribution due to 6 by j omega is a minus 20 dB line passing through 20 log of 6 at omega equal to 1. Now, suppose you had to plot this. So, how are you going to plot this? So, let me just try to plot this using the lines that are present. So, let me use a line here. So, suppose this is 20 log of 6, this point is 20 log of 6. So, this point is 20 log of 6, which is comes out somewhere around 15 point something. So, this is 20 log of 6. Again, see, this is a semi log paper where you see these are, this correspond to 0.1, 1, 10 and all that, right. So, this is 20 log of 6. Now, at 20 log of 6, what did we see? We saw that for 6 by j omega, we have a minus 20 dB per decade line passing through 20 log of 6 at omega equal to 1. So, the line that we will draw must pass through this point. At omega equal to 1, it should be 20 log of 6. So, now we will have to just come up with a line which is of minus 20 dB per decade. So, what do you mean by minus 20 dB per decade? So, for every decade there will be a minus 20 dB drop. So, which means the line will be something like this. So, let me just try to draw the line. So, this is at 20, right. So, at omega equal to 0.1 it is at 20. So, a minus 20 dB per decade line will be like this. This will be the slope, right, because this is that after 1 decade. So, there will be a minus 20 dB drops. At omega equal to 0.1 it is 20 dB. So, at omega equal to 1 there should be 20 minus 20 0 dB. So, this is the minus 20 dB per decade line. Now, this line, let me just change the color just for visualization purpose. So, this line must, so see I am not changing the slope remains the same, must pass through this point. So, the first line due to 6 by j omega will be of something of this form. So, this is a minus 20 dB per decade line. Okay. Now, this is just for one factor. So, we have to look into the other factors also. Now, here are the other factors. So, this was the first factor that we have already talked about. These are the other 3 factors. So, let us look at the other 3 factors. So, this part is gone, this part we have already discussed about. Now, we have 1 by 1 plus j omega, which is this. So, in this case for 1 by 1 plus j omega, the corner frequency, because this is omega by 1, right, corner frequency is 1, and therefore, at omega less than 1 radian per second. So, we will have a 0 dB line, and for omega greater than equal to 1, we will have a minus 20 dB per decade line. Okay. Similarly, for the other factor, for 1 plus j omega by 4, this is coming on the numerator, and see the corner frequency here is omega by t here is 1 by 4. So, the corner frequency is 4 radian per second. So, at omega less than 4 you have 0 dB line, and at omega greater than 4 you have plus 20 dB per decade line. Now, comes the quadratic term, complex pole. Here we have a complex pole here. So, if we have a complex pole, then what will happen? So, we will have to look at the corner frequency. Remember, this was the form for the complex case, right, this was the form. So, here u is equal to omega by omega n is the corner frequency. Corner frequency means the frequency at which there will be a change in the slope, right. So, in this case omega equal to 6. So, omega equal to 6, because you see this is u square. So, u square means omega by 6 whole square. So, omega n is 6. So, this is the corner frequency. For omega less than equal to 6 we have 0 dB line, and for omega greater than equal to 6 we have a minus 40 dB per decade line. So, what I have done is I have carefully written it in a ascending order, okay, so that we get the frequencies in the correct order. You can jumble it up, but it becomes difficult for you to check where are the corner frequencies. It is always better to write it down in a ascending order. So, it will help you in drawing the plot easily. Now, you see this we have already drawn. Now, we will go to the corner frequency 1. So, at the corner frequency 1, for omega less than equal to 1, we have a 0 dB line, which means this factor is not influencing the magnitude at omega less than equal to 1. So, for omega less than equal to 1, there will be no change that will happen to the plot that we drew because of this 6 by j omega factor. Now, for omega greater than equal to 1, there will be a minus 20 dB per decade slope. Okay. So, let us go ahead and see. So, this will look like, so now see at omega equal to, so this will be up to this. So, this is a minus 20 dB per decade line. Now, since this was a minus 20 dB per decade line, now you see at omega equal to 1, there is another minus 20 dB per decade being added. So, which means this minus 20 dB per decade, another minus 20 dB per decade. So, that means we need a minus 40 dB per decade line. Let us try to draw a minus 40 dB per decade line. Let us see. So, first we will draw the minus 40 dB per decade line. So, this is 20. So, this is a minus 40 dB per decade line. Now, we will try to draw this. So, from here it will start. Okay. Now, up to what point will it go? See, after this we had the second factor at 4. So, at 4 there is a plus 20 dB again. So, this will move up to 4, this will go. Again remember you cannot change the slope. I am hoping I have not changed the slope in this process. So, let us see, this is the, so this is the line basically, this is the line that you have. Okay. Now, comes the next point. The next point is at 4 you will have a plus 20 dB line. So, which means you were at minus 40 dB per decade, now there will be again a plus 20 dB line, but we already have a plus 20 dB line. So, let me just use it. So, this is a plus 20 dB line, but from 4. So, from this corner frequency there will be again a plus 20 dB line. Next comes after that we have at 6. So, from omega greater than equal to 6 we have minus 40, from less than 6 there will be no effect. So, for omega greater than equal to 6 we will have plus 40. So, remember, so this is minus 40 dB per decade line, this part. So, this is the part of the plot that will be required, the rest the blue part is not required. Now, from here this is a again minus 40 plus 20. So, this becomes a minus 20 dB per decade line up to 6. So, up to this is 4, this is 5, this is 6. So, up to this. After this then there will be another change. Now, after this what is the change? How much are we expecting? So, again another contribution of minus 40 dB per decade. So, we will have a minus 40 dB per decade line again, something like this, something like this. Something like this. So, that will be a, so minus 20, then another minus 40. So, minus 60 dB per decade. So, we have a minus 20 dB here. So, from minus 20 dB we need another. So, from minus 20 dB we need another. So, minus 20 dB we need minus 20, minus 40, minus 60 dB per decade line. So, we will need a minus 60 dB per decade line. So, let me just add a minus 60 dB per, is there an option? So, this is minus 30. So, this is a minus 60 dB per decade line. So, you can have it somewhere here, something like this. So, as a whole if I take everything together, this is, so the plot will look something like this. Okay. So, let me just draw what are the points we have taken. So, this is a minus 20 dB per decade line, this point is 20 log of 6, then we have a minus 40 dB per decade line, then we have a minus 20 dB per decade line, and with the minus 20 dB per decade line there will be a minus 40 dB at, so minus 60 dB per decade line. Okay. So, this will be the plot for the magnitude part. Okay. What about the phase part? So, for the phase part you see, again remember we will have to look at each factors again. For 6 by j omega there is no contribution in the phase part, the only thing is, so again remember for 6 there is no contribution in phase, right, this is 0 degree phase, but for 1 by j omega the phase is minus 90 degree for all omega, for every value of omega it is minus 90 degree. So, that means 6 by j omega, although as far as slope is concerned it is always 0 degree per decade, however, the starting point is getting decided by 1 by j omega. The starting point will be minus 90 degree, because of 1 by j omega minus 90 will always be there. So, the starting point is minus 90 degree. Okay. Now, comes again 1 by 1 plus j omega. So, if it is 1 by 1 plus j omega, corner frequency was 1, right. So, if the corner frequency is 1, then you have to look at, so see this is the corner frequency, you have to look at 0.1, go back 1 decade and then here go ahead 1 decade up to 10. You must be thinking how did I write 0.4, 0.6, 4, 6, 40, you will see soon why I am writing that. Okay. Once I populate the table, you will know why I am writing those. But for now, this is how you can start. You have started with 6 by j omega. Okay, 6 by j omega, the constant part does not give any phase angle. So, we have only 1 by j omega. Now, corresponding to 1 by j omega, we know that it will be minus 90 degree for all omegas. So, we will start at minus 90 degree. Now, once we have started at minus 90 degree, we go to the next factor, which is 1 by 1 plus j omega. Now, the corner frequency here is 1 radian per second, and if you go back to the table, let us go back to the table. If you go back to this table, see 1 by 1 plus j omega. So, for us in this case t is 1. So, for omega less than equal to 0.1, we have phi equal to 0 degree. For omega greater than equal to 10, we will have minus 90 degree, and between 0.1 and 10 there will be a minus 45 degree per decade line. So, this is what we are going to use. This between 0.1 to 10 we should have a minus 45 degree per decade line. See this table that we are making, we are basically trying to see what is the combined slope. Okay. So, now for 1 plus j omega. So, yeah, for 1 plus j omega, see at we were at 1, go back 1 decade 0.1 and 10. So, you see minus 45 everywhere. So, this is a minus 45 degree per decade slope. Now, at 10 this slope will stop, right. So, therefore, we are keeping it 0. Now, we come to the next one, which is 1 plus j omega by 4. Again at 4 we are starting, go back 1 decade and then go forward 1 decade. These are the points we are entering. So, from 0.4 there is a plus 45 degree per decade line. So, this is a plus 45 degree per decade line up to 10, and then at 40 it will be 0 again. Similarly, for the complex poles, here the corner frequency was 6. So, you start at 6, go back 0.6 and then you have 60. So, at 0.6 you start at minus 90 and then you end at 40, because at 60 it will be 0. So, you see this is the reason I am using 0.1, 0.4, 0.6 and all. So, you can make a table and then you have to populate it this way, and you always keep it in the ascending order so that it becomes easier to plot. Now, you see I can see what is the combined effect of the slope. So, the combined slope will come out to be this. So, if the combined slope comes out to be this, so we have a 0 degree per decade slope, then you have a minus 45 degree per decade slope. You can see the various slopes here. So, if I have to plot it, so let us start to plot it. So, where will we start? See, remember the starting point is minus 90 degree because of the 1 by j omega factor. So, from the minus 1 by j omega factor we will start here. Up to what point we will go? We will go up to 0.1. At 0.1 it will be a minus 45 degree line. So, up to 0.1. So, this is up to 0.1. Okay. Here we will have a minus 45 degree per decade line. So, a minus 45 degree per decade line will be, we already know how to do this, we have already done this for the magnitude case. So, minus 45 degree per decade line will look something like this. So, you will have to go and draw it, and then we have till again at 0.40. So, where is 0.4 for us? This is 0.1, 0.2, 0.3, 0.4. So, up to this point. So, up to this point, then again 0 degree. So, again we have a 0 degree line up to which point? Up to 0.6. So, up to 0.6 we have a 0 degree line, and then again minus 90, you see minus 90 till 10, right, till 10 minus 90. So, again you go for a minus 90 line per decade, minus 90. So, this is a minus 90 per decade line. So, then this will go to up to 10. So, let me just make it a bit larger, yeah. So up to 10. Now you have to be very careful with the slope. I am not carefully doing this, I have to be a bit careful. You see the slope has changed, so you have to be carefully, you have to do this. So this is the slope, and of course this will continue to this point. Then you have the next thing, which is minus, and then minus 45 from 10 to 40, from 10 to 40. So something, this line, something like this will be the slope. So up to 40, and finally what do you have? Again a 90 slope, and then 0, again a 90 slope, again a 90 slope up to 60. So 40, 50, 60. So up to this point, and then you have a 0 slope. So this is the entire thing. So this is a 0 degree per decade slope, then we have a minus 45 degree per decade slope, then we have a 0 degree per decade slope, then we have a minus 90 degree per decade slope, then we have a minus 45 degree per decade slope, and then finally we have a 0 degree per decade slope. And you see, these are the corner frequencies. Okay, these are the corner frequencies. You should write down what the corner frequencies are. These are the corner frequencies, the frequencies at which there will be change in slope are the corner frequencies. So you have to write down what the corner frequencies are. This was 0.4, this was 0.6, this was 10, and similarly you will have here also, this was 40. So here it was, this point was 60. So this is the phase plot corresponding, approximate phase plot corresponding to the transfer function. So this example hopefully helps you to understand how to draw approximate magnitude and phase plots for a transfer function. Of course, this is where you are given the transfer function. It turns out the other way around is also possible, and that has much important implications, because that will also help you to find out the transfer function of a system. We will stop here today and we will continue in the next lecture. Thank you.